In this presentation, the type of titanium alloy and the heat treatment methods required to produce the ideal road bike frame will be explored. Road bikes are a class of performance bikes that focus and attempt to maximize the speed of the bike from a given power input from the rider. The intended application of a road bike is to allow the rider to travel at a distance at a relatively high speed, 25 to 45 kilometers an hour, with minimum fatigue. Certain design assumptions were followed. The dimensions of the bike are as seen below for the size 51 specialized Dolce. And the other components of the bike are also compatible with the frame design. However, in an ideal scenario, the frame should not have the same material properties throughout the bike. For example, the frame of the bike that should have the stiffest properties is around the crank. This is because of the stress concentration around the crank due to the pedaling motion, which can result in small deformations within the frame. On the other hand, the part that connects the rear wheel to the frame should allow for deformations in the lateral direction in order to absorb energy from the ground. This will provide and improve the quality of the ride in order to reduce the fatigue on the rider. And another assumption that we had was that the entire frame would be made from the same grade of titanium with the same heat treatment process and the same cross-sectional area of each tube. And materials required for single-piece casting and molding of the frame are readily available. In order to optimize the performance of the frame should be made in one piece rather than welding the parts separately. This method should be followed since stress always concentrates around the welded joints. Thus, to construct the frame, a cast should be designed for the geometries of the intended mold, and the cast should be also able to handle the high temperatures of molten titanium alloys. And the last design assumption is that the performance is the main priority. For the functional requirements, our main function is that the structure supports the rider and other components of the bike, such as wheels, pedals, gear changing system, and the braking system. Our constraints are to withstand the external forces on the frame with very little bending, which means high stiffness. As well, geometry is specified. Our main objective is to minimize mass, and our free variables are the type of titanium used, the type of heat treatment, and the cross-sectional area of different parts of the frame for aerodynamic purposes.
For our manufacturing process, we selected metal casting. We made the assumption that the maximum length of the hollow tube would be 3.1 meters. We came about this assumption by summing out all the lengths of the parts on the frame. To make our calculations easier, we assumed that the maximum force applied would be 3.1 meter tube. The average mass of a cyclist is 85 kilograms, but since we're manufacturing a road bike, we assumed that the value would be 100 kilograms as the mass of the rider. We implemented a safety factor of 1.4 based on the structure of the frame and the points where the force applied would be maximum. Our main objective for this project was to minimize the mass of the bike. One of the constraints we considered was a specified failure load, which was approximately 1.4 newtons. Our free variable in this case was the outer radius of the tube. After all the calculations had been done, we came up with a mass equation for the frame. There were three elements in the objective equation, and these were the geometric constraints, which includes all the parameters affecting the shape of the frame, the functional constraints, which include all the parameters affecting the function, which in this case was taken to be the force, and the material performance index, which contains the material properties that are needed to attain the objective of this project. When plotting the MPI on the Ashby plot, a slope was constructed to eliminate alloys that do not meet up with this objective. The MPI could be seen in the picture above. When plotting the MPI on the Ashby plot using the CES software, we had to consider some limits to narrow down the suitable material list. Some of the limits we used were the minimum fracture toughness, the metal casting, the durability of the alloy in fresh water, the durability of the alloy in salt water, and in weak acids and in strong acids. On the left side, we can see the plot of the use strength versus the density with the slope being implemented. And on the right side, we could see the plot of the use strength versus the density after the limits had been applied. We can observe that only 3 alloys were remaining, and these were considered in the final results. Another constraint that was considered was the maximum deflection under a load, which is taken to be 0.1 centimeters. After doing all the calculations, we came up with the mass equation, and the MPI can be seen above. We needed to maximize the MPI. On the left side, we can see the plot of the Young's modulus versus the density, with the slope being implemented. And on the right side, we could see the plot after the limits had been implemented, and we had 6 alloys to consider. After analyzing all the suitable titanium alloys, Ti6Al4V was chosen to be the best material, given our constraints and our requirements.
This is the mold and cast method. With the material selection finalized, the metal will then have to be formed into its final geometry. Casting is the manufacturing process in which molten state of a metal is poured into a mold. The mold contains a hollow cavity of the desired shape, which is then allowed to solidify. A mold and cast method was chosen because welded parts lose some its structural integrity. Constructing the frame in one piece will produce a product that will have less stress concentration and will be less prone to corrosion. Excess material from the mold and cast will be removed after the titanium alloy solidifies. The frame will be machined to its final exact geometry by either laser cutting or grinding. This is a phase diagram of titanium alloy. The solid solution that is ideal for Ti6Al4V is the solution containing alpha and beta. Therefore, the solution treatment temperature has to be above martensite start temperature and below transverse beta temperature. To minimize time, the temperature just under the transverse beta was selected. The aging temperature has to be under the martensite final temperature. However, to minimize age hardening time, the temperature just under martensite final temperature was selected. This is the TTT diagram of titanium alloys. The x-axis units are in log per seconds. Y-axis units are in degrees. As seen in the previous slide, solution treatment will be processing at temperature 950 degrees for 0.88 hours or 53 minutes. Age hardening will be processing at temperature 600 degrees for 4 hours and 56 minutes. This is laser powder cladding method. Laser powder cladding mass process is one of the newest technique of coating process. It is used for adding one another material onto the surface of host material. This method is always used to increase the corrosion resistance. By using laser head to melt the surface material powder from powder spray nozzle on the clad area, the material chosen will successfully coating on the surface of the metal. The laser cladding technique offers precise control of the coating on the substrate due to excellent control of the focused laser beam. The cladding process will prevent corrosion, which will ensure that the bike will be able to maintain its structural integrity. That will help us to meet our functional requirements for a longer period of service time.